I'm Dr. Selim Mimarulu. I am Director of Data Science at Oracle. I'll be talking about very accurately estimating solar energy generation with advanced artificial intelligence. At this talk, I'll be sharing our artificial intelligence and machine learning research with you. I will introduce our solar models. I hope you enjoy this talk and find it useful. We have built a range of models that utilize advanced deep learning techniques designed to identify where, when, and how much an appliance is using energy. There are three questions that can be asked and answered by our models. The question of where an appliance is being used on the grid is answered by a presence discovery model. Predicting existence of solar panels or an appliance at a household is referred to as presence discovery. The outputs of our presence discovery models are typically expressed as confidence levels. The question of when solar panels are generating energy is answered by detection models. Predicting when solar panels generating at 15 minutes or 1 hour AMI granularity is referred to as detection. This information is of particular importance to program managers who are interested in managing energy generation characteristics over time. The question of how much energy is being generated and supplied to the household or to the grid is answered by a disaggregation model. Predicting the energy generation by solar panels or energy usage of electric vehicles and appliances at matching AMI granularities is referred to as disaggregation. We have built artificial intelligence models that can automatically and very accurately perform presence discovery, detection, and disaggregation, which are independent of the make, model, and year. All our advanced artificial intelligence models continuously improve over time with more data. At this talk, I'll be focusing on solar detection and disaggregation models. Detection and disaggregation models provide very detailed information at 15 minutes and 1 hour intervals. These models can also deliver information for annual and billing insights. The level of granularity varies depending on the insight needed to deliver. At this slide, I show some of EV and large appliances detection and disaggregation models that we have in our current products. We have many great models. At this talk, I'll be focusing on our solar detection and disaggregation model, which can very accurately predict solar energy generation at residential households without the solar system information. Our models, unlike the physical models, use only readily available attributes as input, such as net energy usage and weather. Therefore, our models apply and reach generally, and I will show this later, but for now, I have to tell our models are much more accurate than any competitor's model or freely available solar software from well-known research organizations. And similar to other models that we developed, our solar models' accuracy improve over time with more data. At Oracle, we have access to the world's largest database of utility data. We transform massive quantities of raw energy usage, device, digital engagement, and transactional data into energy insights and recommendations. We have been working with these datasets for more than a decade, and we understand the specific data challenges. Our advanced artificial intelligence models benefit from being trained on diverse datasets and learning from repetition across different geographies at scale that can't easily be done in-house or with any other vendor. Solar customers are typically high energy users. They are utility aware, they have complex bills, and they are digitally engaged. Solar customers are great candidates for various programs. They like customer engagement, and they are rate aware. How can we automatically estimate solar energy generation? There are many good ways. We will look into two very important methods. One is powerful and recently very popular deep learning, and the other one has been around since 1980s and is based on physical modeling. Let's start with physics-based solar modeling. For this domain, PV Watts calculator is a good example, which has been in development since 1980, well over 40 years. PV Watts calculator requires a lot of system information, which is hard and in some cases even impossible to obtain. We tested PV Watts at several regions using the best default input values for each region. Unfortunately, we see high median error rates in the pie chart that's around 17% overall. Unfortunately, on publicly available reports, we see similar high error ratios from other vendors. Let's switch gears to talk about our modeling approach, which is based on deep learning. Our very low errors improve continuously with more data. Inputs to our model are 15 minutes or 1 hour AMI data and weather features. Note that we don't need or use any system information, which is required by all the physical models and is hard to obtain and maintain. Output of our model is very accurately estimated solar generation. With post-processing, we make this even better and achieve only 3.7% pie chart error for 15 minutes and 4.2% error for 1 hour AMI overall. The errors are remarkably lower than all the physical-based models or any of our competitors. In the next slides, I will show our models in action. In this example, I show our model's results on an unseen home, which means that the model has not seen this house's data, not even partially, or the historic data. On your left, you can see monthly true values in blue. These are the real PV generation numbers. And on the same graph with orange, you can see our model's estimation from July to December 2019. The bars are almost identical, indicating close to perfect results. And now, let's see the hourly insights on the same house for several days for the month of November 2019 on your right. Similarly, in this case, we can observe that hourly predictions are almost identical to true solar generation values. Similar to the previous example, here I show two graphs on an unseen home in Texas. On your left, you can find the monthly solar generation and our model's estimates from March to December in 2019. As you can see, this is not a standard case. Solar generation, surprisingly, is more in fall to winter months. And not surprisingly, our model captures this very accurately at the monthly granularity level. On your right, you can find hourly level insights for several days in November 2019. At this insights level, solar generation values are remarkably close to true generation values. In both cases that I shared, our solar models achieve remarkable high accuracies. Let's talk about some use cases. Solar generation estimation is an important piece of information that can be shared with your customers. This information is known by most of the solar installers, but unfortunately unknown by most of the utilities. Providing this information to your customers discloses both financial and environmental benefits achieved by your customer at a personal and tailored level. You can also use this information for alerting your customers, especially if the solar panels are not efficient due to shading or some other factors, which makes a great tip. Solar generation estimation enables disaggregation. Disaggregation models working on total energy usage will work with net metered solar customers with our model's accurate solar generation estimation. On Solar Home Energy Report, you can provide neighbor comparison and peak usage information. Similar information can also be provided on the data browser. And finally, with the insights provided by our solar estimation model, you can help your customers help themselves to understand their bills better. that can save a lot of calls to your customer representatives. At this talk, I introduced our solar models to you. I also touched on some of the related use cases. I hope you find this talk useful and applicable to your work. Let me know if you have any questions. Thank you.